Okay, the last topics we need to discuss in bonding and structure are polar molecules and hybridization. So if you remember back to the beginning of our discussion of covalent bonds, we talked about the fact that if you have two atoms that are bonded and their electronegativities are great enough apart, so the delta En is greater than typically 0.4, you get a polar bond. So the carbon to oxygen bond is polar. Carbon is the less electronegative atom, so it's slightly positive. Oxygen is the more electronegative atom, so it's slightly negative. So because we can have polar bonds, we can also have polar molecules. However, when we look at polar bonds versus polar molecules, we find that when we assemble these bonds into molecules, polar bonds do not have to give us polar molecules. In the case of CO2, if I look at how the polarity works, this bond works like that. That bond looks like that. So my positive end, my negative end of the bond. So you notice these two things are vectors. They cancel each other out because one's going that direction, one's going that direction. From a chemistry point of view, what that means is that the electron cloud is pretty evenly distributed, so that molecule is non-polar, even though it's made of polar bonds. So when we go to look at something like water, however, we have a different situation. In water, the hydrogen is the positive end and the oxygen is the negative end. Now if you notice, these arrows point toward each other. That means there is a definite negative side to this molecule and a positive side to this molecule. The negative side is over here at the oxygen end. The positive side is over here at the hydrogen end. And if we look at this molecule, the overall trend in polarity is for this side to be positive and this side to be negative. So that would be a positive molecule, a polar molecule, not a positive molecule, a polar molecule, and we say that that molecule has a dipole moment because it has a measurable polarity to it. And you don't have to worry about how we derive those values, but you just need to know that they exist. And how we measure the polarity of a molecule is by throwing polar molecules in an electric field. When we put polar molecules in an electric field, they line up so that the positive end of the molecule is oriented toward the negative pole, and the negative end of the molecule is oriented toward the positive pole. The strength of the electric field required to make these molecules all align like that gives us an indication of how polar the molecule is, and that's how we measure the polarity of molecules. So how do you know if something's polar or not? First, you need to draw the Lewis structure. So all of our discussion on bonding is based around Lewis structures, so you need to be very comfortable drawing Lewis structures. Then you look at the Vesper method to predict molecular shape, and you look at the Vesper notation. If I have a symmetrical molecule, typically those molecules are nonpolar. Asymmetrical molecules are typically polar. That is not always true, but it's true in many cases. So Vesper notations like AX4, AX3, AX5, where 1, I have no lone pairs of electrons, and 2, if the X is the same, so it's all hydrogens or all chlorines or all oxygens or whatever, then those molecules tend to be nonpolar. Asymmetrical molecules tend to be polar because those lone pairs of electrons, just as they do in water, force bonds into certain positions. So those lone pairs of electrons help to contribute to the fact that the polarity of water looks like that. Okay, so now last thing we need to talk about is how do these electrons get shared? Something called valence bond theory says that we have overlapping atomic orbitals. So we just take, here's my hydrogen molecule, we overlap two 1s orbitals, the electrons are shared between them. Seems to work just fine. Well, that works for very, very simple molecules, but even when we get to something like CH4, it does not work anymore. Because when we look at the arrangement of valence electrons in carbon, we find that there are 2 electrons in the 2s and 2 single electrons in the 2p, which would predict that you would make 2 bonds, which would be 90 degrees apart, because p orbitals are aligned along the x, y, and z axis, so they are all 90 degrees apart. But what we observe experimentally is that carbon forms 4 bonds, CH4, not CH2, and those bonds are 109 degrees apart, not 90. So what we say is that these atomic orbitals combine with each other, which is called hybridization. They hybridize to form 4 new bonding orbitals. So these 4 hybrid orbitals are all the same energy and each has a single electron. So let's look at a picture of this. So here's carbon, ground state as an atom. When it's getting ready to bond with something, the first thing that happens is that one of the 2s electrons is promoted to the 2p. So now I have 4 single electrons. Then these 4 orbitals combine to form 4 new orbitals, all of the same energy. And then 1 electron goes in each one. So because I'm taking 1 s orbital and 3 p orbitals to make these 4 new orbitals, I call this an SP3 hybrid structure. And each of these is an SP3 hybrid orbital. So my carbon would be in the middle here, with its 4 equal orbitals scattered around at 109.5 degrees. So in methane, this is what happens. 1, 2, 3, 4. So overlap with the 1s electron. Now over here we have ammonia. So remember, ammonia has that 1 pair on there, but since there are 4, my Vesper notation is AX3E. So I have 4 sets of electrons repelling each other. That is still SP3 hybridization. It's just instead of putting an atom here, I just have a lone pair of electrons sitting in that 1 orbital, giving me the trigonal pyramidal shape. So in boron, we have SP2 hybridization, because in boron, there's 2 electrons in the p. In the atom, we have this. So the first thing that happens is that this pair of electrons splits up. So now I have 3 electrons, and you notice I have this empty orbital. So that orbital stays as a p orbital. These 3 electrons orbitals combine to form 3 equal orbitals. Since I used 2p orbitals and 1 s orbital to form this combination, this is called SP2 hybridization. And the same thing happens with anything that has AX3 or AX2E geometry. Those are all SP2 hybridized, and then the third P does not hybridize. And we'll talk about what happens with that P and some other things that are besides boron here toward the end. So finally, we have SP hybridization. Beryllium in the ground state as an atom, 2s, and then the 2p is empty. So those 2 electrons separate. The orbitals with electrons hybridize to form an sp hybrid, 1s, 1p, and then there are 2p orbitals that stay unhybridized. And then I get sp hybridization. So again, if we want to remember what hybridization is occurring, we look at the Vesper notation, which is based on the Lewis structure. So if I have AX2, so I have linear, I have sp hybridization. These two, which are based on AX3, one central atom, 3 things attached, one central atom, 2 things attached, 1 lone pair. Those are SP2 hybridized. And then when we look at this last set that's SP3 hybridized, you notice there are 4 things around the central atom. Either 4 atoms bonded, 3 atoms and 1 lone pair, 2 atoms, 2 lone pairs. And that gives us SP3 hybridization. We will not worry about hybridization of expanded octets, even though if you look in your book, it's in there, and it talks about things like SP3D, SP3D2. We do not worry about those things anymore. That's a fairly recent development in bonding. So SP, SP2, and SP3 are the only 3 hybridization states you need to worry about, based on the shape, which is based on the Vesper notation, which is based on the Lewis structure. So everything goes back to the Lewis structure. So when we start looking at these hybrid orbitals and what types of bonds form between them, we find out there are actually 2 different types of bonds that form. So one is called sigma, one is called pi. A sigma bond is formed on the axis between 2 bonded atoms. So whenever we have single bonds, they are also sigma bonds. All single bonds are sigma bonds. So again, if I look at a Lewis structure and I count all the single bonds on there, that tells me how many sigma bonds are present. Pi bonds are formed above and below the plane of 2 bonded atoms. So if I have a double bond, it's 1 sigma and 1 pi. A triple bond is 1 sigma and 2 pi's. So every time bonds form between atoms, you always get a sigma bond. If you have more than 1 bond between 2 atoms, that's when you get pi bonds. So no multiple bonds, no pi bonds. So what's happening here, and we'll look at CH4. If we look at the Lewis structure for CH4, it looks like this. If I look at just that carbon right there, there are 3 things bonded to the central atom, 2 hydrogens in the carbon, no lone pairs, so that is AX3, which means the hybridization is SP2. So the SP2 hybridization tells me how many sigma bonds are going to form. So this is an SP orbital, this is an SP orbital, this is an SP orbital. So SP, or SP2, I wrote SP, SP2, SP2, SP2. So those are all SP2 orbitals. The bond is on the plane, lies in the plane between the 2 atoms. Those are sigma bonds. So to get this double bond, remember carbon does have 4 electrons. So the unhybridized p, because remember sp2 means that there's one unhybridized p, has that final electron. And so what happens is the p orbitals of the 2 atoms that are double bonded together overlap. And that's what forms my pi bond. So pi bonds form above and below the plane of the atom. They are not in the plane of the 2 atoms that are bonded together. They are outside that plane. So if I look at this Lewis structure, 1, 2, 3, 4, there are 5 sigma bonds and 1 pi bond. So in this structure, this notation is a little confusing. There are the sigmas equal 5 and the pi equals 1. And there's 1, 2, 3, 4, 5, 6 lines drawn total. The first bond is a sigma bond, the second bond is a pi bond. And this is just showing what's bonded to what. The 1s of hydrogen is bonded to one of the sp2s of carbon. So now when I form triple bonds, what I get is this linear structure, because now I have 2 unhybridized p orbitals. So I get a sigma bond to bond everything together. Then 1 pi bond forms above and below the plane of the carbons, and the other pi bond forms in front and behind the carbons. So I have electrons all the way around this sigma bond that's in the middle. So when I look at this Lewis structure here for acetylene or ethene, I have a sigma bond holding that carbon to that hydrogen, a sigma bond holding this carbon and hydrogen together, and then one of these three bonds is a sigma bond bonding those two carbons together, and then the other two are pi bonds. So in this one I have 3 sigma bonds and 2 pi bonds. Now, when we get multiple bonding like this, we can get something called a geometric isomer. And a geometric isomer simply means there are 2 different ways to physically arrange the atoms. So if you remember back to resonance structures, we always arrange the atoms the same way, we just move the electrons around. In geometric isomers, we move the atoms around. So we have a different geometry depending on how the atoms are arranged. And geometric isomers arise from multiple bonding. So there are 2 types of geometric isomers. One's called cis and one's called trans, which I have a picture here in a second. Typically, where you're going to see them is when you across double bonds in carbon compounds. That's when you're going to see them. Square planar, yes, it can do that, but we don't really worry about the square planar thing because it does not happen that often. So what do cis and trans look like? So I have 2 butene, and remember ENE means there's 1 double bond, and it's right here, it's behind the blue line. So my double bond is right there. So that cis means that I have a hydrogen, the 2 hydrogens are on the same side, and the 2 CH3 groups are on the same side. So if you think about this, if I just draw the Lewis structure looks like this. So flat 3-dimensional 90-degree bond angles, that's not what happens in nature. This carbon is tetrahedral. These 2 carbons are planar, they're trigonal planar, and that carbon is tetrahedral. So what happens is, depending on how you put these things together in 3 dimensions, you get this one isomer where the 2 carbons, the 2 CH3s, carbon and 3 hydrogen, are on the same side, and the 2 hydrogens are on the other side. In this isomer, you'll notice that the CH3s are across from each other. That's trans. The hydrogens are across from each other. That's trans. So those are cis and trans isomers. And in class, we will look at some models of this and talk about this also in a little more detail.